Okay, so we begin our discussion for Module 3 on eigenvalues and eigenvectors. Eigenvalues and eigenvectors. What are the objectives? So at the end of the lesson, you should be able to verify eigenvalues and corresponding eigenvectors. You should be able to find eigenvalues and corresponding eigenspaces. And lastly, you should be able to use the characteristic equation to find the eigenvalues and eigenvectors and find the eigenvalues and eigenvectors of a triangular matrix. The eigenvalue problem. So this is the definition of eigenvalue and eigenvector. Let A be an n by n matrix. The scalar lambda is an eigenvalue of A when there is a non-zero vector x such that A times x is equivalent to lambda times x. The vector x is an eigenvector of A corresponding to lambda. Example number 1. Verifying eigenvectors and eigenvalues. So for the matrix A, which is a 2 by 2 matrix with the entries 2, 0, 0, negative 1, verify that x sub 1, which is a vector with components 1 and 0, is an eigenvector of the matrix A corresponding to an eigenvalue lambda sub 1 equivalent to 2, and that the second vector, eigenvector x sub 2, with components 0 and 1, is an eigenvector of A corresponding to the eigenvalue lambda sub 2 is equivalent to negative 1. Okay, so what we need to do is just in order to verify that x is an eigenvalue of A with corresponding eigenvalue lambda sub I, we only need to apply the rule that A times x should be equivalent to lambda times x. Okay, so doing that, we have multiplying x sub 1 on the left by A produces the vector, the column vector with components 2, 0, which can be expressed as a scalar vector, that is 2 times the column vector 1, 0. So since A times x sub 1 can be expressed as a lambda times x, we therefore say that x sub 1 with components 1, 0 is an eigenvector of matrix A corresponding to the eigenvalue lambda sub 1 equivalent to 2. Similarly, multiplying the second vector with components 0, 1 on the left by A produces another vector, column vector, with components 0 and negative 1, which can be expressed as negative 1 times the column vector with components 0, 1. So since we were able to come up with an A times x is equivalent to lambda times x, we were able to verify that x sub 2 with components 0, 1 is an eigenvector of A corresponding to the eigenvalue lambda sub 2 equivalent to negative 1. Eigenspaces. Theorem 7.1 tells us about the eigenvectors of lambda which form a subspace. If A is an n by n matrix with an eigenvalue of lambda, then the set of all eigenvectors of lambda together with the zero vector, so we have here the set which consists of x, such that x is an eigenvector of lambda in union with the zero vector, is a subspace of R raised to n. This subspace is the eigenspace of lambda. For example, how do we find eigenspaces in R squared geometrically? So we're asked to find the eigenvalues and corresponding eigenspaces of A, which is a 2 by 2 matrix with the following entries, negative 1, 0, 0, and 1. So basically, we have a diagonal matrix. Geometrically, if we're going to multiply a vector with components x, y, in R squared by the matrix A, such that we will have an A times B. We will have, okay, so performing the matrix multiplication, we have the 2 by 2 matrix, negative 1, 0, 0, 1, multiplied to the vector with components xy. We will have negative 1 times x plus 0 is negative x, and we have 0 times x is 0 plus y, we have y. So geometrically speaking, this tells us that we ended up with a vector that corresponds to a reflection in the y-axis. Now, since we will have a negative x, now let's see here in the second slide. So we're given the vector, okay, with components xy, and the multiplication of this vector to the matrix produces another vector with the first component being negative x and with the same y. So the geometric interpretation is just a reflection of this vector with respect to the y-axis. So say here, A simply reflects vectors in the y-axis. For a vector on the x-axis, okay, let's say we will have, if we consider another vector with, let's say y is equal to 0, and multiply that one with A, you have negative 1 times x is negative x plus 0, negative x, and 0 times x is 0, and also we have here plus 0. We see that negative, the column vector negative with components negative x and 0 can be expressed as negative 1 times the column vector x0. Now, since the multiplication of an ax produces an expression lambda x, then again, we can verify that the eigenvalue is equivalent to negative 1, and the vector x0 is an eigenvector of the given matrix. And also, and geometrically speaking, okay, if you're going to go back to the previous diagram, so this will be the given vector, and multiplication of this vector with A results to, again, a reflection of this vector with respect to the y-axis. So for a vector on the y-axis, okay, multiplication of the column vector with component 0y with A produces a scalar vector wherein the eigenvalue is equivalent to 1. And therefore, we can say that the vector with component 0y is an eigenvector of A. So again, so the eigenvectors corresponding to lambda sub 1 equivalent to negative 1 are the non-zero vectors on the x-axis, and the eigenvectors corresponding to lambda sub 2 equals 1 are the non-zero vectors on the y-axis. And we can see it here. So the vectors with components x0 and negative x0 lie on the x-axis, and the vectors with component 0y is simply a vector on the y-axis. Okay, this implies that the eigenspace corresponding to lambda sub 1 equals negative 1 is simply the x-axis, and that the eigenspace corresponding to lambda sub 2 equals 1 is the y-axis, as we mentioned earlier. So that's it about the definition of the eigenvalue and eigenvector. Today, we simply make use of the expression A times x is equivalent to lambda times x to verify an eigenvector of a matrix A corresponding to an eigenvalue lambda. And consequently, based from our discussion, lambda is simply a value that is innate of the matrix A, and therefore it simply affects the vector by increasing its magnitude, no?